In this lecture, we're going to talk about the motion in the presence of resistive forces. So what are the resistive forces and how can we describe the motion in the presence of resistive forces? Actually, in this case, we consider or we take into account the effect or the impact of the medium where the objects are moving onto the object. And this medium can be liquid or gas. So in this case, what happens is that the medium exerts a resistive force on the object that is moving through this medium. And we call this resistive force, or we denote it by capital R. As examples, this could be the air resistance associated with moving vehicles, and we call this air drag. Also, we can mention the air resistance, which is usually associated with the free-falling object. We said that we neglect this force when we study free-falling bodies, but still exists this resistive force. Also, one other example that we can mention is the viscous forces, which act on objects that move through liquids. Now, you have to keep in mind two things, two essential properties of this resistive force. The first one is the direction of R. So R is always opposite in direction with respect to the direction of the motion of the object relative to the medium. So if the object is moving rightward, then R is leftward. If the object is moving upward, then R is downward. This is the first thing. The second thing is about the magnitude. So keep in mind that the magnitude of the resistive force, it depends on the speed of the object in a complex way. So either it's proportional to the speed, and this is in most cases, it's the case for small objects, such as dust particles, for example, falling slowly through air. In this case, we assume or we think that R is proportional to the speed, while for the large objects moving, such as skydiver, cars, etc., in this case, R is proportional to the square of the speed and not just to the speed. Now, how can we write down an expression of R? Let's see. Let's take the simple case where resistive force is proportional to the speed. So assume that we have an object that is moving through a given liquid or gas, just a medium, okay? And assume that the resistive force in this case is proportional to the object's speed. So how can R be expressed? It's in this way. So first of all, forget about the vectors. We can write down that R is equal to B times V. So in this case, we ensure that there is a proportionality between R and V through this factor. So B is just, it's called the proportionality factor. And to make sure that R and V, they are opposite in direction, we have here a minus sign. So this is why the vector R is equal to minus B vector V. And this minus sign makes sure that R and V, they are of opposite direction, while the magnitude of R is just proportional to V through the factor B. Don't forget that V is simply the velocity of the object, and B is just a constant. Now, how can we determine this constant? Actually, it depends on both the properties of the medium, and it depends also on the shape and dimensions of the object. So this B is characterized by these two things, the medium and the object itself. But in any case, B is just a constant, which is a coefficient of proportionality. Now, let's take an example. For example, you have a sphere, which is a ball. It's a small sphere that you release it from rest in a liquid. Now, when it is on the top, and before being released, its acceleration is just g, the gravity acceleration. But once it enters into this medium, then it is actually subject, or it's acted upon by two forces. The first one is mg, which we always have, but the other one is r. And since this ball or this sphere is just moving downward into this liquid, then r would be upward, because r is a resistive force that opposes the motion of the object. So these are the two forces that act on this ball, and this is the vector that shows how V is directed. And we know that it's downward because the object is falling into this liquid. Now, one of the questions is, how can we determine the velocity of the object in this case? Actually, the way we can do this is to apply Newton's second law, because Newton's second law, on one side, it gives access to the forces that are acting on the object. On the other side, it gives access to the acceleration. And the acceleration, don't forget, it's the derivative of the velocity with respect to time. So let's apply Newton's second law in this case along the y-axis for the simple reason that the ball is moving in the vertical direction, and both forces are applied in the vertical direction as well. So this is why we have sum Fy is equal to m times Ay, where Fy are the projections of the forces onto the y-axis, and Ay is the y component of the acceleration. So if we take the y-axis to be downward, because it's just taken like that. I mean, you can take it upward as well, but we have just taken it downward because v is pointing downward in this case. Then we end up with mg plus mg minus b times v is equal to ma. And don't forget that a, we don't have it, but we know that a is nothing else than the derivative of the velocity with respect to time. And so you end up with this equation written as dv dt is equal to g minus b over m times v. And don't forget that this is nothing else than a differential equation. And it's differential in v, but you have v also on the right-hand side of the equation. So now let's just analyze a little bit. Initially, in the initial time, when the ball was still at rest, so v was equal to 0, r was also equal to 0, because I mean the object was not moving just at the initial moment we're talking this about. It was not moving in the fluid, and so there is no resistive force that opposes its motion. In this case, the acceleration was just the gravity acceleration. But at the time, as the time increases or runs, and the small sphere is just moving into this fluid, as long as it moves, R increases, the resistive force increases. And what happens is that the acceleration would decrease in this case. But there is one critical moment, or one particular moment that we talk about, and this moment is characterized by what we call the terminal speed. So this moment is when the acceleration of this object approaches 0. So when the acceleration of the object approaches 0, then in this case, you just end up with an object which has two forces acting on it, which are mg and r. And if the A is 0, then we end up with a resistive force that is almost equal to the weight of the object. So this is why we call this this moment, it's characterized by the terminal speed. So it's the speed that you can reach at the end. And we can write down then in this case just Newton's second law in the following way. So it's plus mg minus bv is equal to 0. But don't forget that in this case, it's not any v that we are talking about. We're talking about the terminal speed. So this is why we have vt. And just from this equation, we can evaluate vt, and we end up with mg over b. And so in this figure, you can see how the object is moving. So at the initial time, the object is not yet into the fluid, and it has an acceleration equals to g. Now, as long as the object or the small sphere is moving into this fluid, what happens is that the acceleration will just will decreases, and the velocity will reach some value which is equal to vt, which we call the terminal speed, which is just a constant. It does not change any longer. So this is one of the examples. Another example, which we just mentioned in the beginning, is the air drag. So we talk about air drag when we have objects that are moving at high speed through air or through fluid. But some examples are, for example, the airplanes or the skydivers or even the cars. So these examples of objects moving into the air, just through the air. And in this case, we express the resistive force in terms of some variables multiplied by v squared. So in this example, which is the air drag, R is equal to 1 over 2 d times rho times A multiplied by v squared, where actually rho is a property of the medium. It's the density of the medium in which the object is moving. A is a property of the object itself. It's the cross-sectional area of the moving object. So it's kind of surface area. And D is just a factor. It's just a constant that we call the drag coefficient. So this is another example of resistive force where R is proportional to V squared. And we're going to see such examples in the applications. So this is why let's move on to see the application. We have here one application about this, part. So we consider an object on which the net force is a resistive force proportional to the square of its speed. For example, assume that the resistive force acting on a speed skater is equal to F, where F is equal to minus K times M times V squared. So you have a minus sign to make sure that this is a resistive force, and F is proportional to V squared through this factor, which is Km, where K is a constant and M is the skater's mass. So you have here two factors. One most likely depends on the medium and the other one depends on the object itself. So the skater crosses the finish line of a straight line race with speed V0 and then slows down by coasting on his skates. You have to show that the skater's speed at any time t after crossing the finish line is given by Vt, that is equal to V0 over 1 plus Kt times V0. So this problem also provides the background for the two following problems. Okay, so it's just for the other problems. So we just considered, in our case, this problem. I'm going to solve it. We have to show that the speed of the skater at any time t is equal to V0 divided by 1 plus K times t times V0. Let me just draw a figure for this. Let's say this is the finish line where you have the final race. So they said that this skater, so the skater crosses the finish line of a straight line race with a speed V0. So let's say that this, at the time it enters into this part, let's say, of the motion where you crosses the finish line, it's given by V0, right? And then as long as you go after the finish line, just you slow, the skater slows down. So it slows down, and it's actually subject to this force, the resistive force. So we know that the sum of external forces that are applied on this object, on this person, which is nothing else than F net, this is called as well F net, that is equal to the mass of the object multiplied by its acceleration, right? Now, we know that the net force in this case is the resistive force, which is given by this expression. So if the object is moving in this direction, it's just V at any time. This is the object is moving into this direction. The object is subject to a resistive force, which is given by F, right? So let's apply Newton's second law on this object. So we know that F net is nothing else than F, right? Is the resistive force, and M, it's equal to the mass of the object multiplied by its acceleration. Now, all we need to do is just to make a projection onto a given axis. So let's take the x-axis. We end up with minus K M V squared is equal to M times A, and A is nothing else than the derivative of the velocity with respect to time. So this, don't forget that this V is the instantaneous V. And so from this expression, we can cancel out the factor M. And so we end up with, don't forget that you have to put the differential of a given variable with the variable itself. And so you end up with minus K times dt equals dV divided by V squared. And now all what you need to do is just to make the integral of these two quantities between the initial time t0 and a given time t. So just make it so the integral of this expression between t0 and t is equal to the integral of this expression as well between t0 and t. And so from here we can deduce that we end up with minus K, so just K is a constant that gets out of the integral. Integral of dt is just t. So we end up with t minus t0 is equal to, now the integral of 1 over v squared is nothing else than minus 1 over v. So we end up with minus 1 over v, and it's integrated between the time t0 and the time t. So you end up with minus K t minus t0 is equal to, so you end up with -1 over v, so -1 over v, so v at the time t, right, minus -1 over, so you just evaluate the function at the two limits, v at the time t0. Okay, now if we take into account that at the time t0, we take t0 to be equal to 0, and v at the time t0 is nothing else than v0. It's called v0 because it's given here. It's the initial time speed. Then we end up with minus kt is equal to 1 over v0 minus 1 over v, 1 over v0 minus 1 over v, where v is the instantaneous, so this is v at a given time t, right? And from this expression, if you just work it out, you will end up with this expression. So let's just do it. We end up with 1 over v is equal to 1 over v0 plus kt, right? So it's given by 1 plus k times t times v0 divided by v0. If you take v0 to be the common denominator, and so from here you end up with v just equals to, so the velocity at a given time t, the speed at a given time t, is given by v0 divided by 1 plus k times t times v0, and this is what you need to show. So this is the solution. And as you can see here, we have taken a resistive force. Okay, they didn't call it R, they call it F, but still it's a resistive force, and this negative sign shows that it's a resistive force, and it's proportional to the square of the speed. So that's it for this part.